Hello everyone, my name is Anna Langstroff and I am from the Department of Plant Breeding in Gießen, and today I will be talking about high-resolution phenotyping of drought tolerance traits in wheat. As you all know, drought tolerance is a very complex trait and therefore we need precise, high-resolution phenotyping of the traits that are associated with water use and transpiration efficiency. It requires real-time phenotyping because this allows to monitor diurnal transpiration patterns such as the regulation of the transpiration around midday in response to elevated vapor pressure deficits. It is also helpful to phenotype across the crop's entire development, as the crop's drought stress response might differ among developmental stages. Such high-resolution phenotyping approaches usually take place under controlled environments because in the field it is usually difficult to control natural occurring precipitation and to expose the plants to defined drought conditions. But such approaches should make sure that they don't lose the relevance for the target environment, which is the field. Therefore, we are using this DroughtSpotter XXL facility. With it, we can continuously monitor the plant's transpiration gravimetrically. Climate conditions such as temperature and humidity are continuously recorded but not controlled. And the large containers that we are using allow field-like plant density and unrestricted root growth. By using a 3D laser scanner that estimates biomass, we are able to non-destructively track plant growth and estimate transpiration efficiency. So this platform enables us to phenotype transpiration-related traits under defined drought scenarios, but still very field-like conditions. For our study, we evaluated 79 elite winter wheat lines for their transpiration behavior under drought stress conditions. At the beginning of heading, all genotypes were exposed to drought stress and all plants were scanned with the 3D laser scanner to estimate biomass growth and transpiration efficiency non-destructively at multiple time points. The aim was to find out if there is genotypic variation for developmental stage specific transpiration efficiency and for transpiration response to elevated vapor pressure deficits. In this context, transpiration efficiency is defined as the ratio of the biomass or biovolume estimated by the 3D laser scanner per unit of transpired water. And as you can see, there is genotypic variation for transpiration efficiency at each developmental stage, and also the ANOVA results show that there is a significant genotype by developmental stage interaction. So we can say that we have successfully identified developmental stage specific variation for genotypes rankings in transpiration efficiency. What is also worth noting is that the repeatability for transpiration efficiency is at each developmental stage quite high. It is assumed that a restriction of the transpiration rate at higher vapor pressure deficits enables the plant to conserve soil water, which results in a higher water use efficiency. To see how our wheat lines respond to elevated VPDs and whether they differ in this reaction, we performed a segmented regression analysis. From this analysis, a breakpoint can be identified, which is the VPD at which the genotype starts to limit its transpiration rate. And in addition to the breakpoint trait, we can also identify the trait slope 1 for the slope at lower VPDs below the breakpoint, and slope 2, which is the slope at higher VPDs above the breakpoint, as well as the difference between the two slopes, which is a measure for how much a genotype changes its behavior. The two graphs show the transpiration rate of two different genotypes plotted against the natural occurring vapor pressure deficits. We can see that the genotype here on the right side restricts its transpiration stronger at higher VPDs compared to the genotype here on the left side. The ANOVA results show that for these traits there is significant genotypic variation at a significance level of 0.1. So to sum this up, with our DroughtSpotter XXL setup, we were able to continuously monitor water uptake and transpiration efficiency under defined drought conditions, but still field-like conditions. And also the resulting high-resolution data enabled us to identify hidden genotypic variation for developmental stage specific variation for genotype rankings in transpiration efficiency, and also for the regulation of transpiration under high vapor pressure deficit conditions. So these are potentially beneficial traits when it comes to breeding for drought-adapted cultivars for a more sustainable crop production. In the end, I want to thank all our project partners, and I want to thank these people who helped with the data acquisition. And I want to say thank you for watching this video, and I'm really looking forward to answer your questions at the Q&A sessions. See you then!